So, welcome to the second lecture on sinusoid and phasors. So, before going into this particular topic today, let me give you one good historical event example. Basically, this is related to a war that happened in late 19th century. So, this war is not a war where fought with the weapons, but it was eventually a war of words. What were those words? Those words were AC and DC. So, at that time lot of debates were going on, that was around 1890 period, that which is superior, whether DC is superior or AC is superior. So, lot of debates and arguments were happening at that time to find out which is better. Eventually, AC won. Why? Because AC was able to transfer the power at a longer distance, losses were less, and it was easier to generate for a higher voltage. So, that is why finally, in around 1895 people accepted AC as a preferred voltage source. So, now let us try to understand why the AC is important in our circuit analysis and why we want to study. So, let us first understand sinusoid. So, basically in this particular lecture we will try to understand the basic concepts which are required to analyze those circuits which are connected with some time varying sinusoidal voltage or current source. So, the sinusoidal time varying excitation means that is excitation given by a sinusoid. Now, the question would be like, what is sinusoid? Sinusoid is a signal that has the form of sine or cosine functions. Now, sinusoidal current is usually referred to as alternating current. So, whenever you say that this is alternating current, that means that you are talking about sinusoidal current that would essentially either in the form of sine or cosine function. Such current reverses at every regular time interval. So, that means it will alternatively become positive and negative. So, the circuit driven by these sinusoidal current or the voltage source are called AC circuits. Now, why we are interested in sinusoids? Because the first the characteristic is sinusoidal, it is alternatively going positive and negative. Sinusoidal signal is very easy to generate and transmit, and right now almost all part of the world the voltage which is generated is AC, and it is being supplied to various loads that may be residential, industrial or commercial. So, since AC is very prominent and it is highly utilized across the globe, we need to understand the AC and the AC circuits which are connected through AC current or voltage source. Now, another important aspect is that using Fourier analysis we can transform any practical periodic signal into sum of sinusoids, and these sinusoids are very easy to handle mathematically because the derivative, that is derivative of sine is cos or derivative of cos is sine. So, it means that the derivative and integral would itself would be sinusoids. So, therefore, the sinusoids are very important for our circuit analysis. Now, let us consider one sinusoid and try to find out what are the various components of the sinusoids. So, how we represent the sinusoid? We represent sinusoid like Vt is equal to Vm sin omega t. Now, t is the time variation, Vm is the amplitude of the signal, and then you have another component called sin omega t, which tells that this particular signal is varying alternatively from positive to negative, because sine function is like this, which is shown in the figure. So, now if you see, there are two figures given in the slide. In the first figure, the variation of the signal is with respect to omega t. Now, here what is omega? Omega is called as angular frequency, which is measured in radians per second. Now, what we are doing in this figure, we are trying to find out the amplitude of voltage signal with respect to angle, because this is omega t, that is nothing but angle. In the second figure, what we are trying to do? We are trying to find out the voltage amplitude with respect to time. So, if you see both of the figures, they are going to be alternatively positive and negative. So, here you see the signal is positive and here it is negative, and again it is repeating after the angle of 2 pi, right. Similarly, if you see the time variation, you will see that the signal is repeating again after the time t. So, what is capital T? Capital T is called the time period of the sinusoid, and after every time period the sinusoid is repeating itself. So, what we can get from these two figures? If you compare both of the figures, we see that the omega into capital T is nothing but 2 pi. So, if you go back to the figure, this is 2 pi, which is nothing but equal to the omega into the time period. So, what we can say? We can say omega capital T is equal to 2 pi, and it can be shown as the time period t can be expressed as 2 pi by omega. So, what happens if you see the signal is repeating itself after time capital T? So, how you will say that it is repeating after every time period capital T? Let us try to find out. So, our say if the our original signal is V small t, we add capital T, that is time period, with small t, that is we have another function V t plus capital T, that is nothing but Vm sin omega, small t is being replaced with small t plus capital T, equal to Vm sin omega small t plus 2 pi by omega. 2 pi by omega is nothing but we saw previously that capital T is equal to 2 pi by omega. So, now if you put the value of capital T in this function, you will get the output as Vm sin omega t plus 2 pi, because if you take omega inside, the first term will become omega t and second term will become 2 pi. Now, what is the value of sin omega t plus 2 pi? It again becomes omega t. So, finally, what we got? We got Vm sin omega t, that is nothing but the original signal Vt. So, in this way we can say if we add capital T in the function, it will eventually becomes the original signal. It means the signal is repeating after every time period, that is capital T. So, we can say that V has the same value at any point t plus capital T as it does at small t, and that is why it is periodic. So, in general form what we will say? We will say that if any function f t is equal to f t plus n capital T, so that is the time period multiplied by any integer value. So, if this particular condition is satisfied, it means that our signal is periodic. Now, as we have seen that capital T is nothing but time period, and using this we can say that the function is periodic function. Now, let us try to find out another quantity which is called cyclic frequency. In general terms, we do not say like a cyclic frequency, we simply say as a frequency, right. So, what is frequency f? F is nothing but the value of 1 by capital T, that is time period. Now, if you put this value in the equation which we derived, that is capital T is equal to 2 pi by omega, what we get? We get omega is equal to 2 pi f. So, this is basically the relationship between angular frequency, that is measured in radians per second, and your cyclic frequency, that is measured in hertz. So, another generic term, because if you see the generic term in the literature, you will see that it is given like V t is equal to V m sin omega t plus phi. So, we add another term called phi, which is nothing but the phase of that particular waveform. What does it mean? If you see this particular figure and you see the voltage V 2 t, so its waveform is not starting from 0, it is starting from somewhere before 0. So, if you put value of t is equal to 0, you will get some value called V m sin phi. It means that at time t is equal to 0, this signal has some value. So, that is why it is having some positive value at time t is equal to 0. So, that means that it is starting before the 0 value. So, that is nothing but the origin we say in the common terms. So, now if you compare with another signal which is V 1 t, and V 1 t is nothing but our original signal which we considered previously, that is V 1 t is equal to V m sin omega t. If we plot both of them, so this will become V 1 t is nothing but V m sin omega t, which starts from origin, while V 2 t is V m sin omega t plus phi, which starts before origin. So, what we can say that the angle, that is phi, is giving some leading edge to the voltage V 2, and that is called our phase angle. So, what we can observe, V 2 is leading V 1 by angle phi, right, or we can say V 1 lags V 2 by phi. Now, if angle phi is not equal to 0, that means voltage V 1 and V 2 are out of phase, or if we make phi is equal to 0, then voltage V 1 and voltage V 2 both waveform will coincide and they will reach at their maxima and minima at the same time. So, this phase difference will define that how two waveforms are out of phase with each other. Now, sinusoid can be represented either in sine or cosine form, and it can be transformed from one form to other form using trigonometric identities. So, before going into the details, let us see few of the trigonometric identities which you will keep on using while you work on sinusoids as well as phasor. So, let us see the first one. What is first one? First one is sin A plus B. So, what you will write sin A plus B? You will write sin A cos B plus cos A sin B, right. Now, instead of sin A plus B, if you are asked to find out the value of sin A minus B, what you have to do? Simply you have to replace plus with minus, that is sin A cos B minus cos A sin B. Now, for cos A plus B, what you will write? You will write cos A cos B minus sin A sin B, right. So, opposite to that, if you are asked to find out the value of cos A minus B, what you will write? You will write cos A cos B plus. So, the signs in both of the cases are opposite to each other. So, it will become cos A cos B plus sin A sin B. Now, using these you can find out few values which are important in our sinusoid as well as phasor calculation. What are these values? One is sin omega t plus 180 degree. What is the value of sin omega t plus 180 degree? That is minus sin omega t. Similarly, if you are asked to find out the value of omega t minus 180 degree, still the output will remain same, that is minus sin omega t. Now, what is cos omega t plus 180 degree? That is again minus of cos omega t. So, here also if you are asked to find out the value of omega t minus 180, again the output will remain same. Similarly, if you are asked to find out the value of sin omega t plus 90 degree, what would be the output? It would be cos omega t. Now, instead of plus, if we say that find out the value of omega t minus 90 degree, now this will become minus of cos omega t, right. So, if it is minus, then your output will be minus of cos omega t. Now, for cos omega t plus 90 degree, this will become minus sin omega t. Similarly, cos omega t minus 90 degree will become plus sin omega t. So, what you can do? You can verify these values by putting values in this particular original formula. So, what you can do? You can put omega t, you can replace A with omega t and B with 180 degree or 90 degree, whatever the case would be, and you will find out these expressions. And these are very important because you will keep on using them when you try to find out the value of sinusoids, like if you want to change sinusoid from sine to cosine, or if you want to find out the value of phasors, which we will discuss in next few slides. Now, let us take few examples so that you can better understand the concepts of sinusoid. Let us take the example of one sinusoid, that is V t is equal to 12 cos 50 t plus 10 degree. Now, you can easily compare this with V m cos omega t plus phi. So, when you will compare, you will come to know that what is V m? V m is nothing but 12 volt, because V is measured in volt. Then what is the phase angle? Phase angle would be 10 degree positive. Now, angular frequency, that is omega, you will get equal to 50 radians per second. So, time period would be omega upon 2 pi by omega, that will become 0.1257 second, and frequency will be opposite to the time period, that is you will get 7.958 hertz. Now, if you are asked to calculate the phase angle between two voltage signals, that is V 1 is equal to minus 10 cos 50 t plus 50 degree and V 2 is equal to 12 sin 50 t minus 10 degree. Now, in order to compare these two, both of them either have to be sine or cosine. So, what we are doing? We are trying to find out the phase angle by converting sine into cosine, and we have to convert the minus sign also into the positive sign with the help of some trigonometric operation we just saw in the previous slide. So, what we can say? V 1 is equal to minus 10 cos 50 t plus 50 degree can be converted as plus 10 cos 50 t plus 50 minus 180 degree, because cos omega t minus 180 degree will become minus cos omega t, as well as cos omega t plus 180 degree will also become minus cos omega t. So, in this case there are two possible options. One is V1 is equal to tan cos 50 t plus 50 degree minus 180 degree, as well as tan cos 50 t plus 50 degree plus 180 degree, because whether it is plus or minus, your output would be minus of cos of that angle. So, we are taking both of the cases and we will justify that in both of the cases we will get the same output. Now, V2 is 12 sin 50 t minus 10, that means 12 cos 50 t minus 10 minus 90, that we are trying to find out the value of sin omega t in terms of cos. So, what we can say, sin omega t is nothing but cos of omega t minus 90 degree, right. This is what we saw in the previous slide. Now, if you use this value, this particular expression will become 12 cos 50 t minus 10, that is 50 t minus 10 is anyway coming from here, and then you just add minus 90 degree. So, in this way you are converting the second voltage signal from sine to cosine. So, V1 what we got is tan cos 50 t minus 130, because the value was plus 50 minus 180. So, it will finally become minus 130, here it will become plus 230. So, these are the two signals which we have computed. Now, V2 you can simply write 12 cos 50 t minus 100, because that is minus 10 minus 90. So, it will become minus 100. You can change this value as minus 130 plus 30, so that you can easily compare both of them. Similarly, you can also write 50 t minus 100 also, 50 t minus 100 plus 360. 360 degree is nothing but 2 pi. Signal being a periodic signal, you will eventually get the same signal. So, we are taking that particular establishment into the consideration, and we are adding 360 degree, and finally, we get 12 cos 50 t plus 260. So, now if you compare these two, you will come to know that V2 is leading by 30 degree. So, V2 angle of V2 minus angle of V1 will be 30 degree. Similarly, for these two cases, if you compare both of them, again you will come to know the angle of V2 minus V1 is equal to 30 degree. So, whether it was plus 180 degree or minus 180 degree in case of V1, we found the same answers. Similar exercise can be done with the help of converting cos into sine and then comparing with the voltage V2. So, that is something which you can do it as a exercise. Now, let us come to another concept called phasor, because sinusoids are easily expressed in terms of phasor, which are more convenient to work with than the sine or cosine functions. So, how we will define? Phasor is a complex number that represents the amplitude and phase of sinusoid. So, if you are asked to define the complex number, what you will write? You will write complex number z is nothing but equal to x plus jy. So, j is the operator which has the value equal to under root of minus 1, which says that when it is attached to one particular value, then this particular value will become imaginary terms and this will become a real term. So, this is basically the rectangular form of the complex number z. The same z can also be expressed in polar coordinates or in exponential form. So, that is r can z can be simply expressed as r angle phi, that is nothing but r into e to the power j phi. Now, what is e to the power j phi? That is called Euler formulation. What does it mean e to the power j phi is nothing but cos phi plus j sin phi. So, this Euler formula is very important for phasor definition. So, we will use it most frequently in our various phasor calculations. So, what will happen, z will be equal to r cos phi plus j sin phi. So, if you decompose, it will again will become x plus j y, where x is nothing but r cos phi and y is nothing but r sin phi. So, in this form r is considered to be the magnitude of z and phi is the phase of the complex number z. Now, if e to the power j phi equal to cos phi plus j sin phi, cos phi can be represented as real terms of e to the power j phi and sin phi can be represented as imaginary term of e to the power j phi. So, in each representation it is normally chosen according to the ease of use, that is either you will use the rectangular form of the complex number or the polar form, that is exponential form of the complex number representation. Now, if you want to add or subtract the two complex number, it is better to go with rectangular form, or if you want to do multiplication or division, it is better to go in the polar form. So, it is possible to convert the phasor from one form to other form. So, if you are given in the form of rectangular, that is x plus j y, r would be nothing but equal to under root of x square plus y square, and the angle, phase angle of the complex number would be equal to tan inverse y by x. Similarly, if you want to convert polar into rectangular, then x will be r cos phi and y is equal to r sin phi. Now, how you will represent sinusoid into phasor form, because this is very important aspect of our circuit analysis. So, we have to understand carefully. Cos phi is nothing but real of e to the power j phi, sin phi is imaginary of e to the power j phi. So, we will use them for a given sinusoid, that is V t is equal to V m cos omega t plus phi, and convert them into phasor form. So, what will happen if you write V t is equal to V m cos omega t plus phi. So, real term of that, because we know that cos phi is equal to real of e to the power j phi, we can write this same expression as real of V m e to the power j. Instead of phi, what we will write? We will write omega t plus phi. So, this will become real of V m, then e to the power j phi you can take out. So, it will become V m e to the power j phi into e to the power j omega t. So, we write this expression as real of V, that is capital V into e to the power j omega t. What is capital V? Capital V is nothing but V m e to the power j phi. So, that is nothing but the phasor representation of the sinusoid. So, in short form we write as V m angle phi. So, in this way the capital V bold which you see in the slide is the phasor representation of sinusoid. So, what you can say, phasor is a complex representation of your magnitude and phase of a sinusoid. So, important thing to see here is that although e to the power j omega t is an important term, but we do not explicitly mention, because in phasor notation we always see this particular term as a time varying component. So, we drop this particular component for the simplicity, but while you do the phasor notation you should always keep in mind that this term will always be present and the frequency of phasor will be omega. Now, to get the phasor corresponding to sinusoid, what we do, we first express the sinusoid in the form of cosine form. So, this is also very important point, because whenever you want to present phasor in present sinusoid in phasor terms, it has to be first converted into cosine form. Why cosine form? Because this is the real part of our Euler expression. This will ensure that sinusoid can be written as a real part of the complex number. When time factor is removed, whatever is left is the phasor corresponding to that sinusoid. So, in short, what we can say that the signal Vm cos omega t plus phi, which is written in time domain, can be converted into phasor domain with taking Vm and angle phi. So, simply you can say V is equal to Vm angle phi to convert sinusoid into phasor domain. Now, if you represent graphically, then if you take two phasors like V is equal to Vm angle phi, I is equal to Im minus theta. So, how you will represent graphically? You will take real axis, imaginary axis, you plot V, V has angle phi with respect to real axis, right, and current I is minus theta with respect to real axis. So, this is the voltage V phasor is leading while the current I is lagging. Now, if you see with respect to time, both would be rotating with respect to the stationary plane, that is the real and imaginary axis plane, right, because we dropped e to the power j omega t term, but eventually the both of the phasor would be rotating in the frame and having the constant angular frequency. That is why they are always constant with respect to each other, but rotating in a absolute term. So, for simplicity, what we say, we do not represent omega for the phasor, because that is seems to be understood, and we simply represent voltage and current as a phasor. Now, if you compare for both of the domains like time domain and phasor domain, Vm cos omega t plus phi can be written as Vm angle phi, Vm sin omega t plus phi is written as Vm angle phi minus 90 degree. Why 90 degree is coming? Because this is in sine term. So, you have to convert them into cosine term, and then you will get Vm angle phi minus 90 degree. Similarly, Im cos omega t plus theta would be Im angle theta, while Im sin omega t minus theta would be Im angle theta minus 90 degree, because sine you need to convert into cosine before converting into phasor domain. Now, before closing, let us take a couple of examples. If you are asked to transform the sinusoid I is equal to 6 cos 50 t minus 10 degree to a phasor, what you will do? You will simply compare it with the standard sinusoid, then you will come to know that in phasor term you have to just represent as the amplitude and the phase angle. So, what will happen in this case? Amplitude is 6, phase angle is minus 10 degree. So, we will write 6 angle minus 10 ampere as a phasor representation of the given sinusoid. Now, if you are asked to find out the phasor value of minus 4 sin 30 t plus 40 degree, first what you have to do? You have to convert it into a standard cosine term. So, that is Vm cos omega t plus phi. Now, using trigonometric identity, what you will write? Since you know that minus sin phi is equal to cos phi plus 90 degree, you will use this formula here and you will convert this into cosine terms, and then it will become 4 cos 30 t plus 40 degree plus 90 degree. So, now what you will write in phasor terms? The phasor terms, the value of this sinusoid is 4 angle 130 degree volt. Now, if you are asked to transform a phasor into a sinusoid, what you will do? You have to first see what is the rectangular, since this is given in rectangular form, you can simply convert it into Euler form or polar form. So, what will happen? The magnitude I m, that will become root of x square plus y square. So, x, y, these two terms are given. So, I m will become 5, then angle theta is nothing but the y by x. So, this will become tan inverse minus 4 by 3, that comes out to be 126 degree 87 minute. So, therefore, you can simply write in phasor form, current I is 5 angle 126 degree dot 0.87. Now, it is very easier to transfer the phasor into a sinusoid. You have to just simply put this value in place of amplitude and this as a phase angle. So, now finally, what will become? I is equal to 5 cos omega t plus 126.87 degree. So, with this we close our today's session. Thank you very much.